This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Gymnasium one? I think so. The Wednesday. That should be. Yeah. But he was interesting, very interesting. So he was a good teacher.
I think I missed the first half of the series. I had to try and catch up every Wednesday.
Yeah, I missed once before too. I found out about that situation.
So I only thought like they had these July lectures in physics. Every Friday they have these lectures in the month of July. And I think that was it. There was no public lectures of physics or anything at the university. But then it seems that they have something gymnasium lectures as well.
I haven't been to these before, but I've been to some lectures here, just like lectures, free public lectures, so it's interesting. But, so yeah, the book, every time I've gone, it's been packed.
Oh yeah, I know.
So they are very good.
Yeah. I'm just trying to figure out what to study for physics. I want to go back to school.
Yeah. Do you like cosmology? That seems familiar.
I mean, I don't know. Some part of me wants to do geophysics. Some part of me wants to just try to figure out what to, where to grab.
Yeah.
Get the whole concept.
I did electrical engineering so years ago.
Yeah, obviously.
But yeah, it's a lot of what optics would dictate my whole work up there. So I don't know if you enjoy what you're doing working, it's not working. It's good. So to me, it was a bit of a steer on what I did, what I know.
Do you still work as an electrical engineer or do you change tracks?
No, I'm really mechanical engineering now.
Like study for?
No, for work.
Oh, for work, okay.
Yeah, so yeah, originally I was always electrical and worked for a number of consultancies, and then ended up sort of just trying to quieten that down, not anything too stressful.
That's interesting.
Yeah, I'm just doing mechanical drafting and things now, so which interests me. So like drawing 3D, so I'm doing the 3D projects and things and all that sort of stuff. That's what I play with. So.
Did you complete your education here at University of Melbourne?
I did an apprenticeship first, electrical electrician. And then I went back to school and did the electrical engineering.
Interesting.
Yeah.
I always wanted to be an engineer, but I'm stuck with being a BSc, a scientist. I don't like to call myself a scientist, but that's as close as I can get.
Yeah, Bachelor of Science.
A Bachelor of Science, yeah.
Yeah. I know you just people are interested in it. A lot about there is you need qualifications to do X, Y, and Z. But yeah, you can still get in there and do things.
So how was doing engineering back in your time?
It was hard. I wasn't great at mathematics, so that's one reason I ended up doing an apprenticeship. But I loved it when I got back into uni. So I didn't get the top marks. I got some distinctions, which were not highs, things like that. But yeah, I got through it. Liked it, but it opens heaps of doors compared to electrician. So
I've always loved the idea of being an actual engineer, as opposed to, a lot of people, they start off as electrical or mechanical engineers, but then they shift to IT for some reason, because it's not hard on the back. Or
Well, that's I'm a physical electrician. I put a physical department.
Yeah.
It's different. You need to go off tools and do something. So that was something that I did.
That's interesting. I mean, I would love to have a career like you. Be an engineer. Just like I hated the idea of going to IT, because it's good money. You sit on a desk, you sit in an air-conditioned room, and you.
But IT cover different disciplines.
Yeah.
Engineers use computers for everything. Sure, scientists use computers for everything. So you need IT. I don't know. I love computers, but I don't know technical things.
That's me. Even though I have a BSc in computer science, I don't really feel like doing IT. That's why I keep coming back.
So what are you doing now?
I work at Monash. I do IT support at Monash. So, and I have a research project at Monash, which is trying to understand how plate dynamics beneath the Australian plate, the Australasian plate, so to say. I'm trying to understand how plates function and how we are able to model them using laws of physics.
I've been to a few things people do with that sort of stuff for development things.
Oh, yeah.
I want to know how the structure work.
Yeah.
What's happening there. So,
You can actually redirect those resources to it's a technique called ambient noise tomography. And you can also so it's a bit like sonar, but with some physics involved. So instead of sound, you use light waves. You just capture images at different frequencies and try to relate what's going on. So it is trying to board and find coil which is available, and then you can have a lot of cash. There's a startup doing that. I think in Adelaide, they're trying to search for minerals on the moon.
that would be an astronaut if they was talking about it.
Yeah.
They've done measurements of the see what's underneath.
Yes, they've done measurements. Like they have some data, and they're attracting funding because of this reason that they want to go to the moon and they want to extract the critical minerals
From everything.
from the moon. I don't know how they will do it, but it's actually a very good start.
How there is in
That'd be interesting.
Their next fleet for such reasons. So the biggest place.
Oh, you want
Wrong side.
I guess I could do.
Okay.
Back then would be coffee, it's still a bit wouldn't be
Okay.
No, you're wireless, yeah, and then I'm HDMI probably. So it's just one of two. There we go. Perfect, thank you.
I'll put that one up. Oh, well.
I suppose it's a spare one here. My laser pointer has given up on the batteries. Oh no, hang on. Oh no, we're good. It was just loose. I used it not that long ago. So yeah, it's just come loose.
What you have is much smaller.
Probably know what his job it is anymore. I forgot until I put my watch on and then I suddenly noticed.
Welcome everybody to our now 4th Gymnasium lecture. There's 2 more next week and the week after, always Wednesdays at 5:30 here in the Herkus Theatre. Today we have with us Dr. Peter Cox. Peter is a lecturer here at the School of Physics and his research area is theoretical particle physics. And today he will be talking about the forces in the early universe. Thank you, Peter, for coming.
Thank you.
Take my...
Okay, so welcome everyone to the School of Physics. So thank you all for coming. So today I'm going to take you on a little bit of a journey through the early history of our universe, okay? And it's going to have a little bit of physics that you might have seen before, talking about our 4 fundamental forces, but perhaps applied in an area that you might not have thought about or might not have seen before, okay? And so let me start with this figure, and I'm going to come back to this a few times throughout this talk. And this is showing us the history of our universe from the very beginning over here on the left, starting with the Big Bang, going all the way out to where we are today here, 13.8 billion years later, okay? And I'm going to kind of step you through some of the key epochs, some of the key changes that have happened through the history of our universe and through the lens of the physical processes that are happening at these various points in time, okay? And looking at how the 4 fundamental forces have played a role in shaping the universe that we have today, okay? So before I start talking about the history of the universe, let's just back up a little bit and remind ourselves what our fundamental forces are. I expect most of you will have seen some, or if not all of these before. So the first one we have, of course, is our electromagnetic force, our force that acts between charged particles. A couple of kind of important facts about this force. The electromagnetic force is a long-range force, okay? You can have 2 charged particles very, very far apart, and there'll be an electric field between them. There'll be a force between those particles. And that force follows Coulomb's famous inverse square law, okay? You might have seen this before. If you haven't, don't worry. There's not going to be many equations in this talk today at all. But Coulomb's law just says that the force between 2 charges is proportional to the charges and inversely proportional to the distance between them, okay? Another force we're probably all very familiar with is gravitational force, okay? Gravitational force between 2 massive bodies. Once again, this is a long-range force, and similarly, it follows Newton's famous inverse square law, okay? Gravitational force is the weakest of our fundamental forces, but yet it can still play a very significant role when we have very, very massive objects, which we obviously do throughout the history of the universe, okay? So the force is proportional to the masses of the objects. The 2 forces that you might be slightly less familiar with are, firstly, the weak force, sometimes the weak nuclear force. The weak force is a short-range force, okay? In contrast to the electromagnetic and gravitational forces. And it's responsible for things like radioactive beta decay, okay? And we're going to see that again a little bit later on. Final force we have is the strong force, all right? Strong nuclear force. And the strong force is quite different to the other forces here. And it's something that we call a confining force. And we'll see a little bit more what this means later on. The strong force is responsible for binding the constituents of protons and neutrons together. So protons and neutrons form the nucleus of our atoms, but they are not elementary particles themselves. They're made up of more fundamental constituents, and the strong force is responsible for binding these constituents together. The residual strong force is also then responsible for binding the protons and neutrons together into the nuclei, okay? So these are our 4 fundamental forces, and we're going to see how these play a role in shaping our universe. Okay? So whenever you've encountered these forces before, you've probably thought about them in terms of these force laws, or maybe in terms of gravitational or electromagnetic fields. But when we're talking about forces between elementary particles on the very microscopic quantum level, these fundamental forces can actually be thought about as being transmitted by quanta, by particles, okay? And so there is a particle associated, or particles, with each of these four forces, okay? In the case of the electromagnetic force, this is just the photon, okay? Photon is the particle that makes up light. We have our wave-particle duality for light that you might have encountered. And the photon is also responsible for transmitting the electromagnetic force at the quantum level, okay? And there's a little diagram here to try and illustrate that. If you have two electrons coming in, they can exchange a photon between them, and that exchange of a photon is transmitting the electromagnetic force, okay? Similarly, for the weak force, we have some particles that are associated with the transmission of the weak force, or weak interaction, and these are called the W and Z bosons. There's actually three of them. We have a positive and negatively charged W and a Z, okay? For the strong force, we have the gluons. In fact, there's actually 8 gluons that are responsible for transmitting the strong force. For gravity, we don't know. We don't yet have a full quantum theory of gravity, so we don't know if there's a particle that is responsible for transmitting the gravitational force. People sometimes refer to it as the graviton, but we haven't actually observed this. We don't know if such a particle exists, okay? Gravity might not behave in the same way at the microscopic level as the other forces do, okay? So we have our particles that transmit our forces. These are called force carriers. There are several other elementary particles that I want to introduce you to today. And so these particles form part of what we call our standard model of particle physics. And the standard model is basically the theory we have that describes all of the fundamental particles and their interactions on the most small and smaller scales, okay? And this is a mathematical theory that can describe these interactions quantitatively. Here I'm just going to introduce you qualitatively to the various fundamental particles that we have in this model, okay? And some of these are going to feature later on in the talk. First set of particles we have are what we call the quarks. And there's 6 of these, named the up, down, charm, strange, top, and bottom. And the quarks feel all of the fundamental forces. They interact via the strong force, the weak force, and the electromagnetic force, okay? The next set of particles we have form part of what we call leptons, in particular the charged leptons. So these carry electric charge. They interact via the electromagnetic and the weak forces, but not the strong force. And one of these particles you'll be very familiar with. This is just the electron, okay? The other leptons we have are the 3 neutrinos, which you might also have encountered. Neutrinos interact only via the weak force, okay? Neutrinos interact extremely weakly. They're very hard to detect. And so the experiments that we do have that can observe neutrinos tend to be enormous great detectors, because the probability of any given neutrino interacting is extremely small because they only interact weakly, okay? All of our regular matter, our atoms, is made up of just particles from this first column here. We have the electron, and then we have the up and down quarks that are going to be the constituents of our protons and neutrons, okay? So all our regular matter is made up of this first column here, okay? The other quarks and charged leptons behave in very similar ways. They just have much bigger masses, okay? So as we go across these columns, the mass is just increasing, except for the neutrinos, all of which are very nearly massless, okay? And there's one more particle we have in our standard model. It's not going to play a role in what I want to talk about today, but for completeness I wanted to mention it, and it's also the most recent particle, elementary particle that we discovered. This was first seen back in 2012 at the Large Hadron Collider, okay? And it was predicted about 60 years before that, and it took us all that time to finally pin it down and observe it for the first time. So these are the particles, the elementary particles that we have in our universe, okay? So, with that preamble, and ingredients that we're going to need for the rest of this talk, we're going to go back now to our picture of the history of the universe, and I'm going to start right over here at the beginning. Now, we don't really know what happened at the very, very earliest point of the universe, okay? We have some ideas, but we don't know for sure. One thing that we think happened is there was a period of something called inflation. And this was a period of very, very, very rapid expansion at the very beginning of the universe. At the end of that period is essentially where we have our Big Bang. The universe gets populated with a very hot, dense plasma of all of the elementary particles that I just mentioned, okay? And so we're going to start our journey there just after this hot Big Bang and talk about what happens as the universe evolves from that point onwards, okay? So as I just said, after this Big Bang, the universe is very hot, it's very dense, and we have a plasma full of all these elementary particles, okay? And the temperature is so high at this point that all of these particles are racing around basically at the speed of light, okay? At the same time, the universe is expanding, okay? And as it expands, it cools, okay? So this is kind of shown here in this little cartoon where we have our initial Big Bang, and then this is illustrating slices at each time. And as we go forward in time, the universe is expanding and its temperature is decreasing. So time and temperature we can kind of use synonymously here to describe the evolution of our universe. As we go forward in time, we're going down in temperature. Now, I want to say a little bit about what it means for the universe to be expanding, okay? Because this is a little bit counterintuitive. We're not imagining that the Big Bang occurred at one point in our universe and then that the particles spread out from that point. That's not what this looks like. Instead, the Big Bang is happening everywhere at once, and it's the universe itself that's expanding, okay? Now, this is a little bit hard to visualize. The best kind of analogy to think of is inflating a balloon, okay? If you imagine 2 points on the surface of a balloon, as you inflate the balloon, those points move apart, not because they're moving along the surface of the balloon, but because the surface itself is stretching and expanding, okay? And a similar thing is happening in the universe. It's the space itself that's expanding, not the explosion within it, okay? Okay, so we have our universe. It's very hot, it's very dense, it's expanding, and it's cooling. The first thing I want to talk about, the first kind of key stage in our universe, is where we form our protons and neutrons. So far we have all these elementary particles, these quarks, bouncing around, interacting with each other. And at some point as the universe cools, it actually undergoes a phase transition. So this is not dissimilar to the types of phase transitions that you might have encountered between, say, a liquid and a gas. Similar idea, but a little bit different here, okay? So to start with, in this hot, dense universe, we have our plasma of these elementary particles, our quarks, and our gluons, and they're all interacting, flying around freely, okay? And as the universe cools, they go through a transition from this plasma phase into a different phase where all of the quarks and gluons are bound up into protons and neutrons, okay? So we have our neutron here, consists of an up and 2 down quarks bound together with the gluons that are mediating the strong force. And similarly, the proton consists of 2 up quarks and a down quark, again, bound together with these gluons, okay? And we say that the strong force is a confining force because once you go through this transition, you can no longer see free quarks and gluons. If you try and pull two quarks apart, the force between them gets stronger and stronger. They want to remain confined inside our protons and neutrons, okay? This process, this transition, happens very, very early on in the universe, when the temperature's about 1,000 billion Kelvin, and about 1 microsecond after that initial Big Bang, okay? So this is happening very, very early on in the process. Now, we can't observe this directly in the universe, it happens too early, but we can create similar conditions actually in the laboratory. We can create a mini Big Bang, if you like. And people have been trying to do this at CERN, at the Large Hadron Collider. So this is an image of the Large Hadron Collider. It sits 100 meters underground on the border of France and Switzerland near Lake Geneva, and it's 27 kilometers all the way around, okay? And inside here you have two counter-rotating beams of particles that are accelerated very, very close to the speed of light and then smashed together at 4 different experiments located around this ring, okay? And one of these experiments is the Alice experiment, which is kind of shown here. This is an enormous detector. You might not quite be able to see. There's a person standing down in here to give you a bit of a sense of scale. So the particles come in and collide somewhere down in the center here. And what this experiment is trying to do is trying to recreate conditions very similar to what we had in the early universe to create this plasma of quarks and gluons, okay? So normally, most of the time at the Large Hadron Collider, they collide protons. When we discovered the Higgs boson, it was in proton-proton collisions. This is a good way to discover new particles. When you want to create these very dense environments in the early universe, we actually do something slightly different, and we collide lead ions, okay? You have 2 beams of lead, and you smash them together. And when you do, you have an event that looks something like this. So the beams are colliding right in the center here. You create a very, very hot, very, very dense plasma that then expands out rapidly, and each of these lines here is a different particle that was produced in this collision and is then measured in the Alice detector, okay? So in these experiments, we're able to create something that's at least similar to the conditions in the early universe and study these kind of exotic phases of matter that we otherwise wouldn't have access to, okay? So we've talked about the strong force playing a role in the formation of protons and neutrons. Let's now talk about the role that the weak force plays in the early universe. So we're going to jump forward a little bit to a time of about 1 second after the Big Bang. Still very hot, around 10 billion degrees Kelvin. And so the weak interactions convert neutrons into protons and vice versa, okay? For example, through processes like this, where the neutron can decay into a proton, an electron, and a neutrino. And if this occurs inside a nucleus, this is nothing but beta decay, okay, which you might have seen before. Of course, here we don't have any nuclei yet, so this is just a free neutron that can decay. We can also have processes like this one, where we have a neutron coming in, colliding with a neutrino to produce a proton and an electron. And in the very early universe, these processes are happening rapidly, back and forward, interchanging protons into neutrons and vice versa, okay? As the universe cools down, though, eventually the rate of these processes slows down and becomes inefficient, and at some point we no longer get conversion between protons and neutrons anymore. And this point happens around this time of 1 second or so. And so from this point onwards, the relative number of protons and neutrons is fixed, and this is determined by these weak force processes, okay? And it turns out that you end up with about 7 times more protons than you do neutrons, okay? The reason that there's more protons is just that the neutron is a little bit heavier than the proton. That's what makes the difference here, okay? Now this number is important because when we go to the next step, which is going to be forming our elements, forming our nuclei, the number of neutrons versus protons that we have is going to change what types of nuclei we produce and in what quantities, okay? So that's the next step, okay? The formation of the first elements, okay? So how do we produce these elements? We're starting off with just protons and neutrons. Well, the process is quite similar to what happens in the sun. We produce these elements through nuclear fusion, okay? So again, the strong force is playing a role in this process as well. And so, for example, we can start with a proton and a neutron. These can come together and fuse into a deuteron, an isotope of hydrogen with one proton, one neutron, and release some energy in the form of gamma rays, in the form of light. Okay? That's the first stage. Can then go on and have two of these deuterons come and collide together. And through this process, you can build up larger nuclei. For example, helium-3 nucleus. So helium has 2 protons. This isotope has 2 protons, 1 neutron. And the extra neutron is just left hanging around and goes on its way. Okay? Similarly, you can step forward again and have this helium-3 collide with a deuteron to produce helium-4, which is the most common, the stable isotope of helium with 2 neutrons, 2 protons, and then you have a proton left over that goes on its way. Okay? And these are just an example of some of the nuclear interactions that are going on. There's a whole set of them that are all interplaying together to produce these different isotopes, these different elements, and you can also produce some slightly heavier elements as well. Okay, so there's plenty more interactions that are contributing here, but I won't go into any of those details. Let me show one slightly more technical plot to give you a bit of an idea of how this process goes. Okay, so don't worry if this looks like there's a lot going on. It's just to give you a little bit of an idea, and we're going to step through it really slowly. Okay? So on this plot, left to right, the universe is cooling down. So time is going left to right. Okay? And what's shown on the vertical axis is the fraction of the mass that's in each type of element. Okay? So things up the top, that's what most of the mass is in. Things down the bottom, we have a tiny, tiny amount of them. Okay? We start off over here initially with just protons and neutrons. Okay? As time goes on, we have these nuclear reaction rates happening. There's some slightly complicated evolution in the middle. And at the end, we're left with, again, plenty of just free protons, or hydrogen, quite a significant amount of helium, and then almost nothing of anything else. Okay? So after this process, we end up with about 75% hydrogen, 25% helium, and a tiny amount of lithium. And that's really it at this point. So this process is called Big Bang nucleosynthesis. We're building the smallest nuclei during the Big Bang. Okay? But as you can see, we're only getting the very, very lightest elements out of this. So where do the rest of them come from? Okay? Well, the answer for that is stars. Okay? So from the Big Bang, we have hydrogen, quite a bit of helium, and a tiny bit of lithium. The heavier elements are all produced in stars. The lighter ones in low-mass stars, kind of like our sun. The heavier elements in here are produced in supernova explosions. Some of the even heavier elements further down the periodic table we think are produced in collisions between neutron stars. In these collisions, you have very neutron-rich environments that helps you to produce some of these elements. And of course, right down the bottom, we have the very heavy elements that don't exist at all in nature and are just produced here on Earth. Okay? So this first process that's happening in the early universe, we're only producing a very, very small fraction of the periodic table. Most of that is going to come much, much later in the history of the universe. Okay? So far, we've got hydrogen, we've got helium, but we only have nuclei. We haven't got any atoms yet. Okay? At this point in the universe, it's still too hot to form atoms. We just have nuclei and electrons flying around in a plasma. So here we have protons or hydrogen nuclei electrons and photons all flying around, and these are scattering off each other via electromagnetic interactions. Okay? And at these temperatures here still, if you were to produce, say, a hydrogen atom by a proton and electron coming together, it's still too hot. The photons that you have around here would then ionize the hydrogen and break it up again into separate protons and electrons. But as the universe continues to cool, eventually that doesn't happen anymore, and at a temperature of around 3,500 Kelvin, or a time of around 380,000 years, we've jumped a long way forward now, okay? We have another transition where we go from this plasma state with separate protons and electrons, and these can finally come together and bind via the electromagnetic force into neutral hydrogen atoms, okay? And this happens at this key time of around 400,000 years after the Big Bang, okay? So there's a few actually interesting and key things that happen around this time in the evolution of the universe. And one of the most interesting things is this point, around 400,000 years, is the earliest point in the universe that we can directly observe. Okay? A little bit earlier, we actually can indirectly observe it. When I talked about the formation of the light elements of the nuclei, we can actually measure the abundances of these out in the universe, and they agree very well with what our model predicts for, say, the fraction of hydrogen versus the different isotopes of helium, okay? So we can indirectly say that we're pretty sure that Big Bang nucleosynthesis happened because our model that predicts these abundances agrees very well with what we see observationally. But now, at this point in the universe, we can actually directly observe, okay? And the key thing that changes is because our hydrogen has now formed into atoms, the universe is now transparent to light. At every point before this, the universe was opaque to light. We had this plasma, and in a plasma, photons can't travel very far before they interact, and so they can't propagate all the way to us today. From this point onwards, light is free to travel through the universe, okay? And the light from this point in time has to travel for 13.8 billion years before we can now observe it today in our telescopes, okay? And something interesting happens to that light as it travels across the universe. And the reason this happens is because the universe through which it's traveling is expanding, okay? The space is expanding, it's getting stretched, if you like. And so as this photon, this wave, propagates through that universe over this long period of time, its wavelength also increases. It gets stretched due to this expansion of the universe. So if you start off with a photon with a wavelength like this, as it propagates, that wavelength gets stretched, okay? The wavelength increases as light moves through this expanding universe, okay? And so frequency of light is shifted towards the red end of the spectrum, okay? The frequency decreases. So if we have light that was originally, say, in the visible part of the spectrum, it gets what we call redshifted. And in the case of this light from the very, very early universe, it gets redshifted all the way down into the microwave band, okay? And we call this light the cosmic microwave background, okay? You look out into the universe and you can see this background of microwave radiation, okay? This light was emitted when the universe was still quite hot, when these hydrogen atoms have just formed around 3,500 Kelvin, but by the time it reaches us, due to this redshift, we observe it as nearly perfect black body with a temperature of 2.7 Kelvin, okay? So black body just means that the intensity of the radiation is a function of wavelength or frequency. Its spectrum is characterized solely by a temperature, okay? And this plot here is actually showing data from the COBE satellite. These black points are the data, and the line through it is a black body spectrum at 2.7 Kelvin. And you can see the line passes perfectly through all the data points, okay? The CMB this cosmic microwave background radiation is an almost perfect black body. Okay? We can do something a little bit more interesting perhaps though, or take it one step further, and we can look at a map of how this radiation varies as we look across the sky, okay? And that's what this is. So this is a picture from the Planck satellite, okay? Satellite in orbit that's observing this background of microwave photons, and this is an image of the full sky, okay? And what you're seeing here, what the different colored regions are showing, is the slight differences in temperature when you look in different directions, okay? So these red regions are directions in the universe that are slightly hotter, slightly denser, and the blue regions are slightly cooler or slightly less dense, okay? But these differences are very, very small, okay? The temperature differences from the reddest spot to the bluest spot here is about 1 part in 100,000, okay? So in actual fact, when you look out across the sky, this background is incredibly uniform. We just have these very, very tiny fluctuations on top of this uniform background of radiation. Okay? And it's these little fluctuations, these tiny variations in density, that are actually going to be the seeds that end up forming the structures in the universe that we have today, okay? So this is kind of the starting point that seeds all of the structure that we end up with when we look out into the universe today, okay? There's another thing that you can get from this picture, not by staring at it. You have to do a lot of work, but from this data, you can actually extract the different types of energy and matter that we have in the universe today, okay? And you can come up with a chart like this that tells you what the energy budget of our universe is today, okay? And you can actually get that just from that image of this background radiation. And it turns out that it's not quite what you might expect. Everything we've talked about so far, all this effort we went to talk about the formation of the elements and atoms, this whole process, only gives us 5%. All of that matter, everything we know, the atoms in stars, gas, dust, everything, only makes up 5% of the energy of the universe today, okay? And in fact, it doesn't even make up the majority of the matter in the universe. 85% of the matter is something that we call dark matter. And I'm going to say quite a bit more about this in the next part of our talk. It's going to play a very key role in developing structures in the universe. The other 70% is something even weirder that we call dark energy, and I'll say a little bit about that right at the very end, okay? So what is dark matter? Well, dark matter, I already told you, makes up about 85% of the matter in the universe. And galaxies are situated inside a halo of dark matter. So for example, here we have our own Milky Way spiral galaxy sitting here. And it's the part that we can see, the stars, the luminous part of the galaxy, is sitting inside a giant halo of this dark matter, okay? And in fact, that halo is so big that it also encompasses some of our satellite galaxies that we have around the Milky Way, things like the small and large Magellanic Clouds. Okay. What do we know about this dark matter? Well, we know that it interacts with ordinary matter through gravity. That's how we know it's there in the first place, okay? We can see it and infer its existence through its gravitational effects. We know that other interactions with ordinary matter or with light must be very weak or non-existent at all. Hence why we call it dark, okay? Not a very imaginative name, but that's what it got called. We also don't really know what it is, okay? We have lots of ideas, lots of theories. It could be a new fundamental particle, in addition to the ones I showed you at the start that make up our standard model. Or it could be something different, like a very small black holes that were produced early on in the universe, okay? Both of these are possibilities that people are actively looking into. And in fact, this is what I spend quite a significant amount of my time working on in my research, is thinking about what dark matter could be, coming up with new models for it, and working out how to test those models. Okay? So I said that we know that dark matter is there through its gravitational interactions. One way that we can measure the amount of dark matter is by looking at that picture of this microwave background. The other way we can do it is by looking a little closer to home at individual galaxies. Okay? And here's a little animation showing two simulations of a spiral galaxy. And the one on the left has no dark matter, and the one on the right has a dark matter halo. And if you look carefully, you'll notice the one on the right is spinning much, much faster, particularly out towards the edge. Okay? These outer regions of the spiral arms are spinning much more rapidly. And we can go and observe both our own Milky Way and other galaxies and look at the stars and see how their velocity varies as a function of radius from the center of the galaxy. And what we find is that it looks much more like this picture on the right than it does the one on the left. Okay? The motion of the stars requires this extra additional source of matter, this dark matter, to explain their motion. There's an additional gravitational force acting on those stars that can't be accounted for just from the stars and the matter that you can see visibly. Okay? Okay, so let me come back to our history of the universe and reorient ourselves. Okay? We started over here at the beginning. We've gone through the formation of protons and neutrons. We talked about nucleosynthesis and the formation of the nuclei through nuclear fusion. We talked about the formation of atoms and the cosmic microwave background. And so now we've ended up here. Okay? And from now on, we start to see a universe that starts to look like the one we recognize today. We start forming the structures that we see when we look out into the universe. Okay? Up until this point, the universe has mostly been dominated by very fast-moving particles and radiation. From this point onwards, matter is going to play the dominant role, and in particular the dark matter. Okay? So that matter is going to start to collapse under gravity. From here onwards, gravity is the main force in the game. All right? So here we have a simulation showing the evolution of the early universe. So on the left here is showing the dark matter, and we're evolving forward in time. And what's going on here is the dark matter is starting to collapse under gravity, and it's forming these structures, these filaments, and these bright spots here, which are regions of very, very dense dark matter that are going to collapse and form our halos for our galaxies. On the right here is shown the gas, okay? The regular matter. And you can see these bright spots here are aligned with the bright spots, the dense regions of dark matter. So our dark matter collapses, and then all our gas falls into that gravitational well that's been created by the dark matter. And as it does, it heats up, and it starts to form stars and galaxies, okay? And as we go forward in time, we're now at 4.5 billion years. You can see these overdensities getting brighter and brighter, these regions where we have galaxies and clusters of galaxies, okay? You might also have noticed these explosions over here. This is where we have galaxies with supermassive black holes at their center, the most energetic engines in the universe, if you like, that are throwing out gas and material into the universe, okay? And so now we're pretty much coming into the late universe, 8 billion years. We have these really prominent structures, these bright clusters of galaxies, and these filaments in between, okay? And this is now starting to look like a universe that we might recognize when we look out into the night sky, if you have a good enough telescope, okay? And really, all of this here is driven by gravity, right? It's driven by this dark matter collapsing under gravity, okay? So that was a simulation, okay? We call it an n-body simulation. You have lots and lots of particles, and you evolve them through time with gravitational interactions, and you get this rich structure, these filaments and these dense regions that form galaxies and galaxy clusters, okay? But it's a simulation. How does it compare with what we actually see when we look out into the universe, okay? This is not a simulation. This is data from a telescope. This is from the DESI collaboration, and what they are doing is looking out into the universe and observing millions and millions of galaxies, okay? So what you see here in the background is kind of a slice looking out into the universe. We're sitting in the center here, okay? And each one of these little bright spots here is a galaxy, okay? And of course, as you look further and further out, you're also looking further and further back in time, because that light takes some time to reach you from that galaxy, okay? And if we zoom in on kind of a region of this that's relatively nearby to us and look at what that structure of galaxies look like, you see something that's very similar to what we just had in our simulation in a box, right? We have these very dense regions where you have clusters of galaxies, and then you have these kind of filament-like structures interconnecting between them, okay? And so you can do that exercise more quantitatively, compare what you expect from this simulation of dark matter and gravity with what we actually observe in terms of the galaxies in the universe, and they agree very, very well, okay? So in the last couple of minutes, I'm going to say something briefly about dark energy. Now, so far through our history of the universe has been expanding, but gravity was slowly slowing down that expansion over time, and eventually things started to collapse to form structures, okay? For the last few billion years, things have switched around. Dark energy has taken over and is actually accelerating the expansion of the universe, okay? And this is something that we didn't know until relatively recently. This was discovered in 1998 by observing distant supernovae, and it won the Nobel Prize in 2011. So this is quite a recent observation. And it's this 70% of the universe that's in dark energy that is driving this accelerated expansion, okay? And so as we go forward in time, our universe is not only expanding, that expansion is getting faster and faster, okay? And as far as we know, that's going to continue on into the future. But there's still a lot we don't know about what dark energy is. We probably know even less about it than we do about dark matter, okay? So as we learn more about what dark energy is, then that picture might change a little bit, okay? So let me just finish up with a few open questions, things that people are actively still working on in research. First one I've already mentioned is we would really like to know what this dark matter is at the microscopic level. We know how it behaves in terms of its gravitational interactions, in terms of forming the galaxies in the universe, but on a microscopic level, we don't actually know what it is. And as I said before, there's a few ideas. Perhaps the most likely is that it's a new elementary particle of some description, but there are other possibilities such as small primordial black holes. The second big question, what is the dark energy? It might be a cosmological constant. This just means that it's some energy that exists everywhere throughout the universe, okay? Some constant energy that exists throughout the universe that causes this accelerated expansion. But it could be something else, something a little bit more complicated, something that's, say, changing in time. We don't yet know. Another question that's really important for the formation of the universe that I didn't have time to talk about today is why do we have more matter than antimatter in our universe? So for all the particles that I showed you, every particle has its antiparticle. For the electron, we have the positron. For the proton, we have the antiproton, okay? And in the early universe, we expect to have about the same amount of matter and antimatter, and these annihilate away together just to produce radiation. To end up with the universe we see at the end of the day, with just matter in it, there has to be a tiny, tiny little bit more matter than antimatter to begin with, about 1 part in 10 to the 10. Okay? And we don't yet know why. It could be that it was just a coincidence, that was the random initial condition of the universe. We like to think that maybe there's some dynamical mechanism, some reason that explains this, and this is also a very active area of research. And finally, we'd really like to know what happened in the very early universe, okay? Right back at the start, around well before we have the formation of protons and neutrons, okay? Very, very early beginnings. And while we can't directly observe that with light, we might in the future be able to get some information about that by using gravitational waves, okay? And so there are new experiments that people are building. One in particular is called LISA, which will be an array of satellites out in space to measure gravitational waves, and these may be able to tell us something else about the very early universe, because gravitational waves can propagate from those very early times when light can't reach us. So that pretty much brings me to the end. I've taken you today through this story of our universe from the very beginning near the Big Bang all the way through to what it looks like today. Hopefully you've seen some physics you knew in a rather different context, and hopefully it's been interesting to learn about the history of our universe. So I'll leave it there, and I'm happy to take any questions.
The cosmic ray pathway of information, how would that be transposed to looking at the next Is that a simple question to answer?
It's reasonably simple to give a rough idea. In practice, it takes lots of people, lots of time and effort to be able to extract this information. Okay, so the way you have this picture of different fluctuations of hot and cold spots all over the universe. And the way you extract the information from that is you look at correlations between different parts of the sky. So you say, what is the average distance, if you like, between 2 hot spots or 2 cold spots, okay? So you change it from an information that's purely a visual one into something that's in a different space where you're looking at the amount of structure on different distance scales, okay? And from that, you're then able to infer how much dark matter, for example, there is. But it is not a straightforward step. Yeah?
How does dark energy accelerate the expansion of the universe like this?
Dark energy is rather strange. It's unlike regular matter. Regular matter has energy density and it can have pressure, okay? Dark energy has negative pressure, okay? Which is a little bit hard to sort of conceptualize. Mathematically, it's a negative pressure, and that acts in a way to accelerate expansion. It's almost like an anti-gravity in a way, if you like, okay? Rather than things collapsing, they're expanding. It's not very intuitive. Dark energy is very, very different to the other forms of matter and radiation in the universe.
How close do you think we are to finding out what dark matter looks like at microscopic level?
Oh, good question. We have learned a lot in the past 15, 20 years about what it isn't. Okay? We had some really great ideas motivated by our kind of theories and our theoretical understanding of the way particle physics works as to what we thought dark matter was likely to be. And some of those ideas are still being tested, okay, and there are experiments now trying to test those ideas, and they could make a discovery tomorrow. Some of our other ideas we've already ruled out. We looked for them, and experiments didn't find them. So the tricky thing about searching for dark matter is the only thing we know for sure is that it interacts via gravity. And gravity is really, really weak. So unless you have a lot of it, you can't detect an individual dark matter particle through gravity. So we're relying on it having some other type of interaction that lets us find it, but there's no guarantee that it does. Okay, so we have to get a little bit lucky. Yeah?
Where are we with gravitational waves now? Because there was a lot of buzz when the Higgs boson was discovered, and where are we now?
With gravitational waves? So yeah, there was a lot of excitement back in 2016 when we had the first detection of gravitational waves, okay, from merging black holes. And since then we've had a lot more discoveries of merging black holes, merging neutron stars. And one of the interesting things that's happened is when you have merging neutron stars, for example, you can detect both a gravitational wave signal, but you can also observe that event potentially with other telescopes, say in gamma rays or X-rays. And so you can learn quite a lot when you have these events where you can see them both in gravitational waves and through other astronomical observations. So that's one thing that's been happening. The other thing that's going to take a little bit longer, but which is coming in the next sort of 10 years or so, which is going to be really exciting, is the next generation of gravitational wave detectors. So the next one will be LISA, which will be in space, and it will probe a very different part of the gravitational wave spectrum, so different types of objects that it will be able to see that we can't actually do on Earth because there are backgrounds, for example, from seismic backgrounds that you can't get around on Earth. So I think the next exciting thing will be the next generation of experiments.
So where do both these worlds collide? The Higgs boson and the gravitational waves, where do they collide?
They collide in the very early universe. And it depends on what types of models you're interested in. So we have our standard model that we know works very, very well, but there are certain reasons to know that we might want to extend it. We have new particles at higher energies, okay? And in many of those models, those new particles can be related to the Higgs boson, and some of those models also predict gravitational wave signals coming from the very early universe that we might be able to observe in the next decade or so. So there is a connection there between sort of the particle physics that's happening in the early universe and gravitational wave signals that maybe you might be able to observe if we're lucky. Okay.
How far back into the early universe are we able to reliably model without current understanding?
Remarkably far back, okay? You have to, so beyond a certain point, it's a model, right? We don't have any strong data beyond a certain point observationally, but our models can extrapolate back to very, very, very high energies, much higher energies than anything I talked about today. So 10 to the 15 times higher energy than where you're forming protons and neutrons. The theories work perfectly well all the way up to those very high energies. Of course, we don't know what the true theory is there. So we have different models, and you can see what the consequences were for those in the very early universe. Yeah?
What are some of the good pieces of observational data or evidence that we have for that period of inflation being in the early universe?
So one of the best pieces of kind of hints for inflation we have, if you like, is that the universe looks the same in every direction, okay? If you didn't have inflation, what you actually find is if you look at one direction in the universe and the other direction in the universe, there hasn't been enough time in the history of the universe for those two regions of the universe to ever be in contact. And yet they have exactly the same temperature when you look at the cosmic microwave background. And so one way you can explain that is if there was a period very early on of very, very rapid expansion. And so that's one of the best kind of indirect pieces of evidence we have for there being a period of inflation. Okay? It can also help explain some other things, for example, why the universe is actually very, very flat. In principle, the universe could have some curvature to it. We see that it doesn't, and inflation is a way to solve that puzzle as well.
Adding on to that, do we know what caused inflation, or do we have any ideas as to what might happen?
We have some models that can produce a period of inflation. The problem is really that we have too many models. And what we would like to be able to do is pin down and exclude some of those models. And already the data from the cosmic microwave background can do that. It can exclude certain types of models of inflation, but there are still plenty of models that could be the true model. And so ideally we'd like to have more data to be able to distinguish between them.
Do you have a preferred dark matter candidate particle, or like one that you work with most closely?
I have worked on a few different types of dark matter. One, I'll tell you about two types that I've worked on. So one is a particle that looks not dissimilar to some of the standard model particles like the Higgs. Okay, it's a particle that has a mass similar to some of our particles in the standard model, and it interacts through the weak interactions, or something that's very similar to the weak interactions. And those types of models are nice because they can actually give you very straightforwardly the correct amount of dark matter in the universe. Okay? At the completely other end of the spectrum, another interesting type of dark matter is something called an axion. And an axion is very, very different. It has a very, very, very tiny mass, and it actually behaves a lot more like a classical wave than a particle. And remarkably, you know, both of those extremes can perfectly well explain all the phenomena we see for dark matter. So you can have very, very diverse candidates. In fact, the range of masses that could be dark matter is about 80 orders of magnitude, which is one of the reasons why it's very, very difficult to pin down. So that's just two examples that, yeah, that I think are interesting and I've worked on. Yeah?
Going off that, is there any predictions that these different models to dark matter might have that would enable you to look out and see, okay, it's more likely to be this one than this one?
So yes, these different models interact with our ordinary matter in different ways, okay? And so we have different types of experiments to search for these different types of dark matter candidates, okay? So for these ones that are more like our particles in the standard model, the way we search for those is by looking for them scattering off regular atoms in big detectors that you have to put deep underground in order to shield them from all the other cosmic radiation, okay? There are several of these detectors around the world. In fact, there's a group here in Melbourne that are building one in a gold mine out in Stawell, about 900 meters down. And so that's one way you can search for dark matter. Other types of dark matter, you can actually look for astrophysical signals, for example, so signals in gamma rays or X-rays. So each of these dark matter candidates produces slightly different signals that you can go and search for. The challenge is all of these signals are quite rare or quite small and hard to see. So it's taking some time to kind of go through and try and probe these different models. Yeah.
Why are you using lead ions at LHC? Is there something specific? Could it be something else?
I don't know specifically why lead. They also use gold. I think they've also done some runs with oxygen. For most of the run, they're colliding protons. If you want to look for new fundamental particles, protons are better because it's less messy. If you want to recreate those really dense conditions of the early universe, you want something with a lot of protons and neutrons to smash together to try and produce this quark-gluon plasma state.
Do we know much about what forms these like quarks and atoms and other fundamental particles?
Do we know much about?
Like what makes up the fundamental particles?
So the ones I showed you there, all of the fundamental particles that we have observed in collider experiments, okay? So we can produce these particles, for example, at the LHC. We don't always observe in our detector all of those particles because some of them have very, very short lifetimes, okay? Some of them only live for the tiniest fraction of a second, and so what you actually observe is the particles that they decay into, okay? And so you have to reconstruct the original particle, and this is particularly true for some of the more massive particles, but the ones I showed up there are the ones that we have measured. Many of them we've measured quite a lot of their properties quite precisely. Of course, we don't know that they're all fundamental, right? As you probe higher and higher energies, you can smash things together harder and harder, and maybe at some point you'll find that these particles are not elementary after all, and they're actually made up of some other constituents. But as far as we know, all of them are fundamental particles.
Is there any reason we should think of the cosmological constant as like time independent rather than like varying time?
Both are possibilities, okay? The constant piece is one that you can just add into Einstein's theory of general relativity. Famously, Einstein didn't have it there to begin with. He added it in. Then no one at that time knew that the universe had accelerated expansion, and so he called it his greatest blunder to put it back in. And now it turns out that maybe a cosmological constant isn't such a bad idea after all. But it also could be something that's slowly varying in time. We can't yet distinguish between them. Some of these new experiments or new observatories, for example, DESI observations that I showed, this picture with all of the galaxies in it, they will have some sensitivity to try and start to see whether dark energy is really a constant or might be varying with time. But it's still very early days to answer that question.
How close to the conditions of the universe do we get in the
At the LHC, in Alice?
Yeah, if we see quark confinement breakdown as well, or do we see free quarks, or is that not quite close enough?
So they do see this plasma-like state, okay? They see, well, what they see is this shower of particles that comes out of it, and from that they can infer that they did indeed produce this kind of plasma-like state, but it still only lasts for a tiny fraction of a second, right? So it's still quite different to the conditions that you had in the early universe, but yeah, you do produce these kind of deconfined state of matter. Okay. Everyone's...
Thank you very much again.
Hi. Sure.
You mentioned the gravitational wave background with upcoming experiments. Would that have something similar to the redshift that we
Yes. Yeah, absolutely. So the same thing happens to any waves. They're produced with very high frequency in the early universe, and then as they propagate, wavelengths get stretched, and they're actually observed, hopefully, if we see them, as low frequency today.
So what is the way to estimate and find that? What's the sort of frequency?
So it's a bit the other way around. The question we ask is, what frequencies can we detect, and then say what models would give us a signal at those frequencies. Okay, so the current experiments are in the kind of Hertz range. You can actually play it, like the gravitational wave signals we have, you can play it as an audio file and listen to it if you really want. The new generation experiments, the space-based ones, will be lower frequencies, kind of millihertz. That's right.
I just have a question. So, like, how can you make sure actually, like, you know how with the special Einstein, we found out that gravitational force, or what we say this attraction is due to like curvature of space. How can you make sure it's actually not always geometrically not like related? You're talking about antimatter. Something you try to find something to like explain using dark energy, and that's like expanding universe. How do we know it's also not something that is geometrically related to, like similar how we came to understand like the gravity?
Yeah. So the way we do it is all of this is done in the context of Einstein's theory, where you can do this in terms of geometry. And the point is that in order to get the geometry that we kind of observe, you need to have this additional component, this dark energy, in order to get a geometry, or matter, to get the geometry that's kind of consistent with what we see. So in certain cases, if you're just looking at individual galaxies, you can really work with Newtonian gravity most of the time. But you can also do it in the full context of Einstein's general relativity and work through that way.
I don't know if I asked that question.
You're actually building LISA right now?
Yes, it will. No, it's been funded. It's meant to launch around 2030. Whether most of these projects usually run a little bit late, so we'll see whether that happens or not. But it is happening, and yeah, sometime in the next decade, hopefully.
So like the lab assembly in space or something like that, like they did with the ISS or something. You can't take it all.
So it's not so big. It's 3 separate satellites, and you fire lasers between them. But one of the challenges you actually want, where you want to put it, is actually quite a long way away from Earth. It won't be in orbit. It'll be at one of the called Lagrange points. They're kind of special stable points in orbit around the sun. So it's not going to be so close. So when you launch it, you also have to wait a bit of time for it to get there, and then you have to check everything's working, hope everything's working, because if it's not, you can't go out there to fix it. But yeah, so it's not anything as big as like the ISS. You can just launch it, and then you just have to get it into position and commission it.
Thank you.
No worries.
I have a really quick question. It's
Yeah.
just more the cosmic microwave background. How do you know what you're detecting isn't just like sensor waves? Or is that
It's a good question. It's a really tricky thing, especially because microwave, you have to have this is a low temperature, right? You have to be able to see the signal over the noise. And actually, the first time that this was seen was kind of by accident. People weren't looking for it. It was discovered by accident as noise in a device people were trying to build. Nowadays, we've now seen it with multiple satellite experiments with better and better precision, all of which are consistent with each other. So certainly, I'm not an experimentalist, I'm a theorist. You certainly have to work very, very hard and very, very carefully to build detectors that are able to see this. But yeah, it's now been observed in a lot of detail over decades. And so we're pretty sure we know what we're seeing at this point. But, in any experiment like that, you still have to understand your detector and also take into account the uncertainties that come from not having an ideal detector. You're never going to have a perfect detector. And so when they take that image and they infer how much dark matter or dark energy or whatever else they do from it, they have to take into account exactly how well their detector is working.
Yeah, I imagine there's like a whole bunch of filtering that's
Oh yeah. There is a lot of people and a lot of work in the steps in going from that picture to that pie chart.
Yeah.
Very last question. So it's a little bit more career related. So I actually completed my bachelor in biotech last year, but then I have this passion for astrophysics, and I'm planning to maybe be a regional degree so I could end up in college. Because I wanted to astrophysics. If everything went normal, I would have been like graduated with the physics degree, but I did bio.
Yep.
And I don't know if you have time. I know it's like maybe not today. Like, would you be down to like if I could talk to you?
Yeah, absolutely. You can send me an email and you can drop by and we can chat. Yeah.
That would be nice. Because one of my main interests is also like dark matter and then particle physics. And I read you all know your theoretical physics. Yeah. So yeah. So I think like conversation.
Yeah, sure. So usually the pathways depends. Did you do much physics in your? Great.
I only did like physics one because it was biomed is very.
There's not much flexibility, right?
Yes, and like we had like all of my subjects were taken up with like double credits and stuff like that. So I had a very limited. But I did like physics one and what did I do? Astronomy or history, like the electives for physics.
Okay.
But yeah.
So you probably have first year done, but you need to think about doing the second and third year.
Yeah.
And then the pathway to research is then you need to do a master's. And then you can do a PhD. Yeah.
But like I wanted to know a little bit more about the field and how it's because you're a researcher and then you definitely know where the field is heading to, and I want to know a bit of understanding of that as well.
Yeah.
Yeah, I've been reading. I think talking to somebody will be nice.
Yeah. No. Sure. Send me an email. I'm happy to chat. Okay.
Thank you so much.
No worries.
I have a friend who is doing internship at Jackson, which is Japan
Yep.
Aerospace Exploration Agency. He recently went to a place that seems to be called something called a neutrino detector. Can you give me a brief idea for what it does and what it's trying to observe?
Yeah. So did he go to Kamioka? He went to neutrino detector in Japan.
He went to the.
He went to. So
yeah,
probably
he kind of bragged me about it.
He probably went to Super Kamiokande,
Yes, that is.
which is very cool. I used to work in Japan, and I got to go and see the detector, and it's very cool. So yeah, the Super Kamiokande, it's a huge detector of ultra pure water.
Yep.
And they're trying to detect neutrinos.
Yep.
When neutrinos pass through, they can produce electrons or muons.
Yep.
And then those produce light because they are traveling faster than the speed of light in water. So they produce something called Cherenkov light that we can then observe in detectors. And so there's kind of a few things that Super K are trying to do. One of them is to really measure the properties of neutrinos.
Yeah.
So we know that neutrinos have very small masses. And because of this, they do something interesting, which is they oscillate. So as neutrinos travel, they can